right, we're good? All right, well, welcome back. If I get everybody to take their seats. All right, right there. And I click it again. All right, so I wanted to show you the video real quick, just so you can see that, the shred. So you can see we're just dropping in the entire bale into the system. That's the Mezzo shredder. Yeah. And it's on tracks, and it's got this little handheld device that you drive. It's pretty cool. A lot of fun to play with. So it does a pretty good job. Not pretty good job. It does an excellent job of shredding. You want something shredded fast, that is the unit. Yeah.
What's the end goal here? Are you guys hoping growers bring you mulch and you guys process it for them to sell? Like, what's the end?
All right, so the question from the audience is what's the end goal? I'm repeating for the virtual folks that are listening in. The thought process here is, traditional recycling equipment has a problem with the mulch film because of the soil level. So that particular type of equipment the thought process is to be able to use something like that to shred. It's mobile from the standpoint that I was pitching to the state that we can use it in multiple applications, so it's not stationary. I can take it to tire site, to C&D debris sites to help shred. And then also the thought process is, why do you want to transport a lot of soil? It doesn't make any sense if you're transporting 70% soil across the state. Thought process is maybe set up regional collection sites, process, screen, try to reduce that soil level and keep it on the farms, and then densify that product perhaps in some type of bale form or something that then you can then send it to an end processing facility. Yeah, all the eggs.
Recyclers coming online. I mean, if you produce this, where is it going to go?
Well, my ultimate goal for this particular research project was to be able to use it as alternative fuel in a cement plant. I've got cement plants that'll take this all day long if you can reduce that soil level. And they'll eat up every bit that's generated in the state. Not a problem. So. All right, well, let's continue on. This is the last session. We've got 3 speakers. Our first speaker is Pam Krone. She's with the Agricultural Water Quality, or is the Agricultural Water Quality Control for California Marine Sanctuary Foundation. And Pam's going to be talking about, we hear a lot about what's going on in the oceans related to plastics. Pam's presentation is Do Agricultural Plastics Enter the Waterways and Ocean? So, Pam, I'm going to turn it over to you.
Thank you, everyone, to those of you who stayed. I know a lot of people had to leave early, but I appreciate your being here. This has just been a wonderful conference for me. I've learned so much about different initiatives that different people are taking, from Driscoll's and what we heard about their agricultural initiatives to technologies that are being developed, like the chemical recycling technologies, the cleaning technologies, the fuel technologies. It's all exciting to me. The distribution system in Germany and how that is working and might be an example for some of us to follow, where we have very low recycling rates, where we know we have recyclable materials available, and then to the worldwide perspective that many of you have provided. So thank you for all your talks and for being here, trying to be part of the solution. Of course, we're concerned about the solution to plastic and to recycling, because the more of it, the more we can value the plastic products, and rather than thinking of it as waste, thinking of it as a material input for the next cycle of products, I think the more it will be valued and the less of it will get into the ocean. So we'd like to see in that spiral shown on my slide here, less of it to the ocean and to the otters. and more of it to recycling facilities or other end-of-life methodologies like the biodegradable mulch. So I work for the California Marine Sanctuary Foundation. We're a nonprofit, and I work on behalf of the national marine sanctuaries. And I primarily work in California, mostly in Monterey. So as you can see, the agricultural fields are right next to the ocean in Monterey and along lots of the California coast. And there are also waterways coming from inland that also empty into the ocean. So whenever the wind or the water carries plastic particles from agriculture anywhere, the ocean's right there. So what happens once chemicals get into the ocean? So this is a slide from the Monterey Bay Aquarium Research Institute. So what happens to it is it breaks down into smaller and smaller particles from UV penetration. It tends to biofoul and sink, so it changes the density of the plastic and doesn't just float on the surface anymore, but sinks to different levels in the ocean. Another big issue for the ocean is those plastics absorb chemicals to them, persistent organic pollutants like dieldrin and DDT, as well as other pollutants. And so those pollutants adhere to the plastic and also leach from the plastic. And then biologically, that causes a problem as at the lower part of the food chain or all levels of the food chain, actually, these creatures directly ingest the plastic, and it can either, cause them to have a replacement for food with no caloric value, or it can get into their intestines and cause blockages, or it can contain these additives and cause other problems. So it causes all kinds of problems along the food system. So why do marine animals eat plastic? And, why don't they distinguish it from their food? Well, plastic hasn't been around a long time, so they haven't evolved to distinguish it. But to them, in some cases, it looks like plastic. For this jellyfish, that floating bag, it looks like a jellyfish. They can't distinguish it from the plastic, so we find a lot of jellyfish eat plastic. Other animals like this sperm whale feed by echolocation, so they dive down a long way, like 1,600 feet, where it's very dark, and so they make sounds and find their food by that echolocation. And for some reason, plastic sounds like the other foods that they're eating, so they tend to eat plastic. To these storm petrels, it smells like food, so that when it biofouls, it has a sulfurous smell, and they find their food by the same smell. So to them, it smells like food, and they pick it up and they ingest it. And then also plastic just gets into the food web. So plastic gets into the food that they're already eating and travels up the web. So where is plastic found in the marine environment? And really it's found throughout the water column. This was a study done in Monterey Bay by the Monterey Bay Aquarium Research Institute. They transected different levels in the ocean to find out where is plastic predominating, and they really found it all the way from the seafloor to the surface and at all depths in the water column, with the greatest abundance found between 200 to 300 meters. So really it's found everywhere in the water column. And it's also found on the surface. I used to just think it floated on the surface, and I was surprised when this study came out and showed that really it's everywhere in the water column. So everything that's feeding at different levels, where it's the whales that are filter feeding, it's just coming in as they're filter feeding in the ocean. So this is also from the same study, what kind of plastic is found. So they used Raman spectroscopy to determine the type of plastic and the abundance. And the highest percent of plastic found was the PET, but they also found polyamide, polycarbonate, polyvinyl chloride, polypropylene, and some other kinds of plastic as well. So that just gives you an idea of what % of each type they found in this one single study. So where does that kind of plastic come from? So, the study didn't distinguish finely enough for us to be able to answer that question. So I looked at agricultural uses for each of those types of plastic as well as urban uses. And really you can find each of those types of plastic in both agriculture and urban uses. And so they weren't really able to distinguish, where is that plastic coming from, whether it's ag or urban. And also that plastic travels through the ocean on currents as well as coming from the shore. So we also don't know whether it's coming from the Near East, is it coming from Asia, is it coming from Monterey, is it left on beaches, is it coming from the rivers that are inland of Monterey. We really don't know the percents that we probably know that it's coming from everywhere, but how much we don't really know yet. So I did a study with the California Marine Sanctuary Foundation, Monterey Bay National Marine Sanctuary, and California State University, Monterey Bay. And we also got help from UC Cooperative Extension and the RCDs and some others to address the questions of how much plastic is used in the field just in Monterey, because that's close enough that we could, and small enough we could answer that question. Is it getting into the waterways in Monterey? And what can we do about it if it is? And so it ended up in a paper, and if you're interested, that's the website that you can find our paper on. So how much plastic's used in agriculture? Estimates are 2 to 5% of total plastic produced goes to agriculture, and these are some old figures. I guess in the earlier talks we heard about 1 billion pounds is used in agriculture in the U.S. now, and my calculation showed that about 20 million pounds are used in field plastic in Monterey, and my study was limited just to films, to mulch films, drip tape, and hoop house plastic. So I didn't address all kinds of field plastic, just basically those 3 kinds. So how is plastic used in agriculture? And it's just used extensively for so many different purposes. I've talked to a lot of farmers that really want to have a plastic-free field, but none of them that I've spoken to are achieving that goal. Some of them are able to reuse their plastic multiple times and feel they're doing a good job with that, but nobody that I know of is plastic-free. And I don't know that we'd want that to happen just because of the benefits that come from plastic use. We're able to transport our products longer distances, and there's just so many benefits. Cleaner, personal protection, and all these things, all these uses you see all have a value, and that's why plastic is used in that way. So I would like to see plastic replaced where possible, but I think we're a long way out from replacing it. So what are the ways that plastic benefits agriculture? We're more efficient resource use. In Monterey, we've reduced our water use by 80% through increased drip irrigation in the past 8 or 10 years. Weed suppression, which reduces pesticide use, so I don't want to see more pesticide use. A longer crop season, which means more income for the farmer as well as more food for the growing population of the world. Controlling animal entry to the field, packaging and transport, increased yields, and being able to grow in areas we couldn't grow before because we can transport water to these areas. So then I looked at how much field plastic is used by different crop types. This just in Monterey, and this was pounds per acre per year. And this just represents the different kinds of crops grown in Monterey. And I think our 2 important money-making crops in Monterey are strawberries and lettuce. So those are really important crops to us. So why do different crops use different amounts of plastic? Well, basically because with almost every crop uses drip tape. Very few do furrow irrigation anymore or sprinkler irrigation. Drip tape is used in almost every kind of plastic, and in fact now single-use drip tape has come out, and that allows for greater distribution uniformity and lower water use in the field. But if there's 3 crops in the field in a season, that's 3 sets of drip tape, that's getting used. So we see that there's increased rates of plastic use as we develop different products. And the thing with the caneberries is they need to control the environment, so they use the hoop house plastic, as well as using mulch and fumigation tarp. And also with the strawberries, they use fumigation tarp and mulch. And that's why they really use more drip tape or more plastic per year because of the different types of plastic that are necessary for their production. So this is a slide from Cornell University that relates to how difficult is a plastic to recycle, and it depends on both the level of contamination and the type of plastic. So many of you have probably already seen this slide that represents different plastic used in agriculture, what type it is, and how dirty it is. So then we had the question, our second question, after wanting to know how much plastic is used, is does that plastic get into waterways and travel to the ocean, or does it really remain in the field and not become a problem for the ocean? And so we did 2 kinds of surveys to address that question. We did bank surveys where we put a transect on the edge of a stream and collected plastic from that transect and differentiated it into agricultural plastic and urban plastic. We chose locations that were in agriculturally predominated landscapes so that we were hoping to collect mostly agricultural plastic. We chose the same location that's monitored by our cooperative monitoring program, which monitors water quality for agriculture. So they chose the sites, and we duplicated their sites, and they chose them based on their thought that they were representative of water quality coming from agriculture. And at the same site where we did the bank survey, we also put out Newston nets and collected floating plastic from the stream, and we metered how much water was coming through the net so that we were able to estimate the total amount of plastic per unit of water. And these just show the sites. We did monitoring at 10 different sites in Monterey and along the Salinas Valley. This was our findings from the stream bank plastic. So we had 10 different sites. We found different kinds of plastic at each site. We found a lot of little pieces of mulch tape. We found packaging. We found personal protective equipment, gloves and hairnets. We found drip tape and drip tubing, and we found a lot of this strapping tape that's used in packaging. So this is just the ag plastic, the urban plastic, which we also found. I didn't show the slide of that because it was very hard to clean this plastic, so we just did counts. We didn't do weight. This represents our findings in terms of plastic count. This is from all 10 areas, what percent we found. Each had a little bit different findings, but about 80% was pieces of plastic mulch. And then our second biggest finding was strapping tape. We found a lot of pieces of that. And then after that, much less of the other kinds of plastic. So then with the microplastics, what we did was we took them to the laboratory at California State University, Monterey Bay. We separated them into micro and macroplastics, and then you can also see that there's a lot of organic waste from the streams in there, so we did a digest process to remove the organic waste, and then we looked at it microscopically and differentiated into films, fragments, pellets, and foam. And then we found that about 53% were pellets, and so these pellets almost all came from one single site. They're pellets where there's a plastic component around fertilizer in order for that fertilizer to have slow release. So one unfortunate grower probably applied near where we happened to be sampling, and then we had a rain event, and unfortunately his fertilizer washed into the stream, and I think that's why we had so many pellets at that one site. But at other sites we found about equal amounts of fragments, fibers, and film. And what's interesting to me is that when we quantified the particles per cubic meter, the 10 streams, we have variation from 1 to 60 particles per cubic meter. And so I compared that to the findings of the Monterey Bay Area Aquarium Research Institute, and it was the same order of magnitude. So what we're finding in our streams in terms of plastic contamination is on the same order of magnitude as what we're finding in the Monterey Bay in the ocean. So that was interesting to me, that it's very similar. So that said to me that indeed our streams are contributing to the plastic problem, so it is something that we should try to do something about. So we decided that as the California, as part of our work, we wanted to develop a strategy for helping to solve the plastic problem. So how does it get from the ocean, or from the field to the ocean? Well, it breaks apart, and we've heard that throughout the sessions. It breaks apart as you try to remove it. It's very hard to get complete removal from the field. Some plastics just are inconvenient and they get tossed aside. I think they aren't properly contained and removed from the field. People are busy in the field. They have production standards to meet. So taking care of plastics sometimes isn't the first priority. So then once it's tossed aside, it gets carried by wind and water and ends up in the streams and the ocean. So what are some of the solutions? Complete removal from the field. So I was really, I loved the solar shrink that we heard about earlier, that there'd be less breakage, increased vigilance, better removal technologies, and then better systems for transporting, for quickly transporting and getting rid of that, what's in the field and left us on the side of the field, and more quickly getting that out of the field. Recycling, of course, we learned about that all through the conference, and I won't repeat. Replacing it with other products, paper or biodegradable mulch. And I know Driscoll's is doing a lot of work on the paper packaging and other packaging technologies. So a lot of people care about this, including one of the growers I work with only uses paper packaging for his strawberries and many of his finger vegetables. And then encouraging everybody to preferentially purchase and be aware of the recycled content and trying to get their product into the recycling chain. So some of the actions that we would like to pursue as the California Marine Sanctuary Foundation is to continue to be involved with those that are interested in alternatives, like as the soil biodegradable mulch on strawberries, to increase the recycling rate of drip tape. So our waste management facility found that they're getting about 6,000 tons a year of agricultural film and drip tape. And so because drip tape can be recycled, we'd like to see more of it get recycled. You know, it's filling up, it's becoming a problem for our waste management facility, and it has the potential, so let's make that happen. Strapping tape, just because we saw so much of it, you know, it's not being properly disposed of. We'd like to see a recycling outlet for it, but at least we don't want it to be tossed aside. We'd like to see it be contained. Growers will be a big part of the solution, you know, creating a more conscientious removal and recycling, or maybe using other products that are easier to remove and get out of their, get out of the dirt, such as the solar stretch. And then just getting all stakeholders involved. It's not just a grower problem, it's everybody's problem, from the recyclers to the producers, and, the producers accepting extended responsibility, researchers coming up with new products and ideas, sustainability companies including it in their certification programs, and waste facilities trying to divert it and have it not go into the, into landfill, but divert it and have it go to a recycling stream, etc. The good ideas we've heard of the past couple days. So these are some of the people I drew from. So as everybody's been saying, it's not a responsibility of any one person. Just like it takes a village to raise a child, it takes a caring community of many different stakeholders to overcome our plastic pollution problem. So thank you all for coming, and I'll open it to questions.
Any questions for Pam? Yep.
Hi, Pam. Thank you so much for the study. And wow, the plastic mulch is 80%. That's, wow, surprising or not. My question is that what is the feedback from the stakeholders? Like, how did they take this information that the farmers or the producers, like, have you been able to get a feedback from that? And what is the response?
Yeah, so our first step was to reach out to some of the professionals in the field, like the resource conservation districts and UC Cooperative Extension, and those that work with farmers. We're just in an awareness building phase, I'd say right now, trying to build awareness of the problem. And so we reached out to that group, and they all were very appreciative of knowing about the problem. It's an enormous problem. We've reached out to the waste management facility, and they have already started working with Revolution Plastic to try to create that separate recycling stream. Driscoll's was interested in our white paper and gave us some terrific feedback, on other things that we might consider and include in our strategy. So, we're just really in the very early phases of this, but I think even some of the growers have reached out to us. There's one who's done a sustainability certification, and he became part of our biodegradable mulch process. So some of the early adopters that really want to find an answer are willing to trial things. And we had a field day last week where somebody asked the question. It turned out the mulch was working really well and not degrading too quickly. And somebody asked the growers the question, did you think it was going to work like this? And they all said, no, we thought it was going to be a complete mess. And yet they were still willing to try it. So that's, how dedicated they are. It's still not proven whether it's going to completely work or not. But we have people willing to try it. And even one of the growers, somebody said, well, if it doesn't work this year, what happens? And he said, well, next year we'll try something new. So they have the attitude of persisting and recognizing that this, it's going to take a long effort to find what really works.
Wonderful. Well, thank you, Pam. I do want to mention one comment after seeing your slides. It jumped right out at me with the use of perhaps paper mulch in the fields as well as paper packaging. We did a PFAS forum. I don't know if you all are familiar with PFAS. Can I get a show of hands if somebody have heard about this? Aha, that's what I thought. It is, I know you have, David, because you did the conference with us. It is a compound that was developed back in the 1930s by Dow and 3M. And it's been shown to be a potential carcinogen. And so you're going to start hearing more and more about this. And the reason why it jumps out at me on the paper side is there was a big push to get away with plastic straws. And so what did they replace them with? A paper straw. But the paper straw is coated. There was a study by the University of Florida. They looked at 38 paper straw manufacturers. 36 of them use PFAS. So we may be actually creating a bigger problem than we have with plastic. So I just bring that to your attention. So if the farmers start using biodegradable paper or paper mulch in the fields that are coated with a PFAS material, it could be problematic down the road.
Yeah, that's just a super point, is that when we're looking at solutions, we have to do more research and not just accept, oh, it's made from paper.
Yeah.
It must be good. Yeah.
Okay. All right. Thank you. All right. Speaking of research, we're going to jump into our next presenter, Dr. Tim Dawsey, Executive Director for Advanced and Applied Science Technology, Pittsburg State University. And Tim's going to be talking about farmers accelerating research in material science. So, sir, all you.
Thanks, Gene, and thanks to all of you who had the patience to hang in here a little bit. I know it's almost the weekend and close to lunch, so I'm going to be moving through things. I think you said the big button here is the one that moves me forward. So I will be talking about what we're calling FARMS. I will credit Dr. Tim Long with coming up with the acronym, but that's Farmers Accelerating Research in Material Science. And we'll be talking about, I am attending this for the first time. I found this basically as a result of the FARMS workshop that we did. And I will be the first to talk about my naivete in dealing with recycled materials. But you'll see why I find this is very important, and I do embrace that. My naive approach rather than defend it on here. So let's take a look at what we've got. I'm going to talk a little bit about the background. Where did this come from? Because it's a bit of a long story, and I'll tell Gene to grab my elbow because I could talk for an hour on here easily. So yeah, he'll catch me if I get carried away with things. Talk about the concept around the FARMS effort on here, and then the engagement itself, the outcome of it. And then path forward, when I first made this slide, I put a question mark behind it. And then that looked like, well, is there a path forward? And no, my question will be, and I'm looking at this group and those attending virtually for ideas, because I'm coming in this, as I said, very naively, but very optimistically around the approach that we're going to be taking on some things. So some important background. The Kansas Polymer Research Center. How many people in here have ever heard of the Kansas Polymer Research Center? Wow, I'm surprised there was one. And online, I didn't see any hands raised, but I doubt there was much more than one there. The Kansas Polymer Research Center was founded in 1994, and we are a leading institute in the area of bio-based materials, research around polymers made from agricultural products. So whether it's particularly vegetable oils, soybean oils, coconut oils, you name it. If it's an oil, we can make a polymer from it. Those materials coming in there. And this was founded in 1994 by a gentleman you may have heard the name, Dr. Zoran Petrovich. And don't be surprised if you haven't heard of that name, but he is very well known, renowned worldwide in the area of bio-based polymers. And when he was a guest lecturer at the University of Massachusetts Amherst, about the time, and he was out of Serbia, attending there or lecturing there at UMass Amherst when the Yugoslavian Civil War broke out. Basically, the country fell apart, and not a great time to go back to Serbia. So he was hoping to stay in the U.S., and one of the other professors there told him he knew this little university out in southeast Kansas that was looking for a chemistry professor. So Dr. Petrovich took that opportunity, went there, and Pittsburg State University is a small, well, 7,500 students or so, teaching university in southeast Kansas, not a research university. But Dr. Petrovich was definitely a researcher at heart, and he went there. He finally convinced the Kansas Soybean Commission to give him, I don't remember, $25,000 or something to start some research at the university. And the university, and I'm not making this up, actually gave him a bit of a custodial closet in one of the old abandoned dorm areas there. That's where he started the program. working in that program. He continued to build, make presentations, and he got the attention of Cargill, among a few others, and partnered with those, and a lot of great success. He hired Dr. Mihail Ionescu out of Romania, came over. He brought one of the top polyurethane chemists from Yugoslavia, or at the time Croatia, over to support him. I call those the three horsemen that basically built the Polymer Research Center there in Kansas. And here's a list of achievements on here. I mean, basically they've worked with a broad range. Virtually everything we do there is with corporate partnerships. So you'll see a lot of names you recognize, and there are many, many more on here, but Cargill, Samsung, Chevron, Phillips, these are the kind of companies that we do research for and with in there. We shared the EPA's Presidential Green Chemistry Award in 2007 with Cargill for the development of some foams that are used in automotive seating and furniture cushions and so forth. Lots of awards, lots of publications and so forth from it. All of this happened before I joined Pitt State University. Basically, I spent about 40 years in the polymers and plastics industry. I was lucky enough to start out doing research in polymers development at Eastman Chemical Company. As a matter of fact, somebody referred to some PBAT work on there. I led the first development of the PBAT materials for Eastman Chemical Company and the commercialization of those materials. So I've been doing this for a long time. I went from polymers research into the plastics processing arena. I spent a decade working in extrusion, thermoforming, materials and so forth, injection molding, compounding, from that side of the business. And then when I got ready to retire, a friend of mine asked me what I was going to do, and I was like, well, I don't really know. And he said, why don't you go to that little university you like so much over there in Kansas? Because I had been recruiting. I built the technology center in St. Louis, and I had to recruit from there. And so I'd been hiring out of that. I contacted them, and they said, well, we've got an opening at our Kansas Polymer Research Center. Like I said, I was almost 40 years in the business at this time, and I had never heard of the Kansas Polymer Research Center. Joined that team there, and it has been amazing. I wound up spending 3 years as the dean of the College of Technology, and then I stepped away from that to say, hey, let's talk about what we can do with this polymer. We're sitting on a gold mine in the middle of an agricultural economy here, an agricultural economy that no longer has any industry. And so a big industry in the past was mining, strip mining in there, from coal, a number of metals and so forth were mined in that area, and in the 60s, 70s, that was eliminated. So now you've got an area that is economically depressed, that depends totally on an agricultural economy, and that's subject to every drought, freeze, flood, everything that comes in. So you can imagine the impact of that. And I'm sitting here looking at a polymer research center that's one of the tops in the nation, in the world, in bio-based materials. And so why aren't we using the crops, byproducts, waste materials, and doing more with that and really pursuing that? So with that, I was talking to an old colleague of mine who was the director of the Material Science Institute there in Virginia Tech, Tim Long. And he is about as excited about opportunities and dealing with problems, real-world problems, as I am. And so we came up with the concept, and I'll give him full credit for the acronym F.A.R.M.S. That's Tim Long. We said, let's get the farmers, the ranchers, the producers in this 4-state region that we're in together with our scientists, and let's talk about the problems. What are all the problems that we could come, deal with, and where might material science be able to come to play to support them and help them? And so we started out with bringing the scientists and the researchers together. We had 8 scientists from Virginia Tech, along with about a dozen of my scientists there together. And total with the ranchers, we had around 70-ish attendees, I think 75 or something like that, that were just spent all day together in breakout sections talking about the problems. The breakout sessions we started with were livestock issues, crop issues, and chemical issues in agriculture. And then we would go through those breakout sessions, which were facilitated by the Kansas State, what am I trying to say, the county agents, basically the extension agents in there. And so they helped translate. They spoke farming. Most of our scientists don't. If they're just like me, most of our chemists and scientists, not all, but most of us did not grow up on a tractor. So we needed help interpreting things, and that's what the county extension agents did. But after each breakout session, we would come back together and talk about, well, what other topics popped up? And one that kept popping up is what we call what's behind the shed, or the back 40, if you will. You know, these are all the things that we're having to deal with that's just piling up as junk, as we've heard over and over at this meeting. And so we brought this group together in February, late February of 2020, yes. And it was a great exchange of folks here. And as somebody mentioned earlier, one of the challenges was finding a time to bring the farmers and ranchers together. So we had to come in there basically late February, between planting and harvesting is when we could get everybody together in there to talk. We had Dr. Tim Connor from NEFA was a keynote speaker. As I said, the K-State Extension agents facilitated this. And we've already had one grant has been funding around self-healing hydrogels for delivery of crop protection to avoid the migration of materials that are put out there. When we put these materials out, keep them there so they're not running off or whatever. So this is a big part of what, but you know, and down at the bottom, you know, you see one of a quote in the paper that they talked to one of the farmers there, saying he came there out of curiosity, but he was really excited about the exchange, the ability to talk to the scientists directly. And one of the real critical things, and I took this excerpt out of a news release that one of the county extension agents put there, and one of the critical factors, and you know, there's been some of it mentioned, Pam alluded to it here or whatever, is that one of the things we found is that these farmers are extreme environmentalists. Land is what they dedicate their lives to. They live off the land on there. At the same time, these scientists in there were equally as excited about opportunities to improve the environment on there. They were sportsmen. They're kayakers, they're hunters, they're hikers, they're rock climbers. They love to get out in the environment. So one of the things was finding this common ground that was critical to us. And the outcomes of that, and there were pages and pages of these, but one of the key ones that did pop up was recycling. Recycling and upcycling. What can we do with these materials that behind the shed, those old tractor tires, those waste containers, the films that we've talked about so much. And so one team took that as their focus. Dr. Tim Long, along with Dr. Jody Neef, took that on to say this was their particular area. And that's our attention, was to bring these collaborations of the universities together to begin pursuing opportunities to focus on these things. Now, parallel to this, at the same time we were putting this on, I was also pursuing efforts to raise the awareness of the Kansas Polymer Research Center and to increase our ability to have an impact. So one of the things that I was working with NIST on this was, altogether between NIST and EDA this past year, we got about $4 million in funding to come in. The NIST funding on here is about $2.4 million here. It's primarily focused on personnel. I've got to bring in some new blood, some new talented researchers to pass the baton off to from these guys that are getting ready to retire. So that's what this is about here with the NIST funding. The EDA funding, in order to recruit that new talent, those people who are going to be that creative next generation on here, they got to have some really cool toys. So that's what the EDA funding is about buying and upgrading the technology in there. Anything from the scanning electron microscopes to our X-ray diffraction capabilities, our gel permeation chromatography, those kind of things. I got to have new toys to get those in here. And that's not the end of it. We got a number of other cakes in the oven right now as well, working on some extended funding for a number of these. So the concept of NEMA, this is the National Institute for Materials Advancement, and that's the funding that we were getting from NIST and EDA is to stand up this entity here. This NEMA is focused on the 4 states region, basically Arkansas, Missouri, Oklahoma, and Kansas is our area of focus here, looking at this mid-America approach of things. And we're looking at being a center for developing industrially relevant materials technology. One of the earlier slides that I skipped over there a little bit was talking about what we want to focus on are user-inspired solutions. So we're going to the farmers, we're looking to those users to tell us, what do you really need? What is our opportunity? And recycling was one of those key ones. The other piece of it is we're a training ground for our next generation of scientists and engineers. At Pitt State University, one of the reasons I was recruiting from there is that's one of the oldest plastics engineering technology programs in the nation. It was founded in 1969. So we have got graduates everywhere that are highly recruited across the nation. What we want to do is give them job opportunities right in the region there. Again, to develop that economy, to bring those high-tech jobs in here. And it's not like we don't have any plastics processing, but we want to bring more of that into the area to be higher-paying jobs, something to diversify that economy. We want to be then a lighthouse for recruiting those students and researchers, as I said. With the latest technologies in here, some of the top scientists in the nation, and collaboration across the U.S., we're expecting to be able to bring some top talent in there as well. And in order to, we want to be self-sustaining. I don't want to keep going to the well begging for money, although that's part of what you do in the university, is that we want to be an industry resource for advanced technologies. And as I said, most of what we're doing already, we are self-sustaining. We work for corporations, so we are an extension of their research arm. So we typically work under NDAs, and we're very comfortable with that. We also provide analytical testing support. So folks that are wanting to test materials, understand what's going on, make changes, we work under confidentiality, so we do a lot of testing for corporations as well. So with the monies that we got from NIST, we had picked up an earlier grant. I got around $300,000 a couple years ago. We used those funds to take an old, really antiquated plastics processing lab, bought all new equipment in here, so the kids are now working with state-of-the-art equipment that's able to get data we were never able to have data with before, understanding the processing conditions and really knowing what they've got as they walk out, and so they can walk into the job and say, yeah, I've used this type of interface before working with this equipment. So much of this is thanks to both NIST and the Kansas Department of Commerce on here. Again, we are driven economically in this approach. From that, then, those two parallel efforts, the F.A.R.M.S effort, along with the development of NEMA, is we came up, and I'm about to show you my true naivete before I got here, was around the concept of recycling and taking this to the next level. But I've heard a number of things that validated some of our thoughts and some that says, you know what, you're crazy. You need to go another way on this. So, but one of these things on here is to say, and we want to take a regional approach in this for collection, sorting, processing, and producing materials from these items as a whole in here. And you'll sort of see our focus around in here as, again I said, the 4 states region there that we're looking at. So Mid-America Materials Alliance is what we've come up with, and this is what we're currently working on now to put together MAMA on here. I'm a Southern boy, so that rings with me as we're dealing with things. And one of the things here, you'll see my naive concept in here, putting this slide together, is that while I'd like to take this film route out here, out of the fields, take it, collect it, clean it up, reprocess it, blow it, and put it back in the fields. As we've talked over and over, it's not quite that simple. Gene's done a lot of work talking about how do we get the dirt off there. Wow, I would love to be involved with the material science side of that, looking what are the adhesion properties, what do we got to deal with to get these materials out, how does TG come into play in these things if we're trying to clean these materials off. So these are the kind of things. Now, I'm not going to pretend that I think that's going to be a standalone. So we've already got a number of recycling opportunities in the area, and we were just saying the agriculture will have to play in as a part of that ultimately. Again, keep in mind, a big part of the driver on this is we're looking at producing technical jobs in the region. And for us, I think it was really important to get to the farmers and listen. If we're going to do user-inspired research and development and solutions, we've got to know what the problems really are, not something we read in a journal somewhere or we've heard secondhand about. And so we actually took these scientists out on the farms. So part of this was a tour of the farms, the whole calving operation, dairy operations, the crop issues that they're dealing with, so they can physically see these things. And as I said, it was in February, so it was a bit of a cold trip. Ultimately, what that's led to now is that I met a few weeks back, maybe a couple of months ago, with those county extension agents from Kansas State University about, we had talked about maybe doing this again. COVID-19 kind of took the wind out of our sails for a little bit, but we're hoping to be back up and running. And what they told me in meeting with them was, look, you are going to need a bigger venue this time, because the farmers left and went and talked to their buddies about the opportunity and saying, listen, you've got to be at the next one. So we are now looking at a much bigger venue to bring folks in. We also have Arizona State will be joining us in this, as well as Virginia Tech, as we're in Kansas State will continue to provide the facilitators for this with us. We also are hoping maybe we will get one or two other universities in, particularly from the material science and polymers perspective on this, so that we can look at these problems and start to collaborate with these opportunities. And obviously, those 4 states producers, the ranchers and farmers in the arena, are going to be very critical to what we're going to do and how we're going to impact this area. So I very much appreciate everyone that I've had the opportunity to talk with. Those of you, my last slide will have my contact information on it here. Please reach out to me. I'm here to learn, not to teach. So if you got ideas, if I'm going down a road and you can tell me why this is crazy, don't go there. The only thing I ask is but. I'm always looking for the buts, okay? If you're going to tell me it's crazy, tell me but. If you want to do it, here's the way I would go at it. So please reach out to me. Give me advice. If you think you can help, if you'd love to collaborate, let me know. We're excited about this, and we think there's a lot can be done. The plastics problem is a real problem, from the microparticles to simply the massive piles of material that we've seen around. These are real problems. We cannot and don't want to sweep them under the rug. As a matter of fact, right now I use this as a recruiting tool. I literally talk to the students today saying, we've got a problem with plastics. Come help us solve it. I had one young lady when I was a dean over at college. I was touring her around. She knew she wanted to go into an engineering type program. I took her and showed her our mechanical engineering, our electronics engineering, a number of these. I said, oh, there's a great area over here in the plastics engineering tech. And she stopped me. She said, no, I don't want to go. I hate plastics. My response to her was, you are who I need. The problem is not going to be solved by the people whining. It's going to be the ones on the inside that are understanding the problem, that are addressing the problem like you folks are today. And we need those people in the classrooms. Those are the next generation that's got to help us solve this problem. Thank you, and I'd be happy to take any questions or comments.
Thank you. While we're waiting to see if there's any questions, I will tell you that I do see something for you to think about, and that is on the separation of the soils from like the mulch films, right? So I've been told that and I'm not a soil scientist, I've been told that the soils have, I believe it's a negative charge, or it might be the opposite way, it might be a positive charge. But if you've, and the plastics also has a charge to it. So I was wondering whether you couldn't come up with some type of almost like an eddy current or some type of electronic way to separate out the soils. Electrostatic, yeah.
Electrostatics. You could do. I don't know what the charge is on the sand, but there's easier ways. But you can. I mean, the ethylene's going to give you a certain charge. So you could certainly do it, but it'd be tough to do it in a mobile situation, and the moisture content is the biggest problem with E-stat, right? So you got to have a really, really dry, sort of hot material going into those systems.
And that's an excellent point. I'm glad you brought it up, Gene, because as I've been listening, those are some of the things. All of the polyolefins are by nature going to be very susceptible to electrostatic development on here. So you're going to build charges up on there that will hold. Now, the moisture will tend to dissipate that charge quite easily on there. So higher moisture should be lower charge, but as you dry it, you're going to build that up. So you got the moisture is going to drive the adhesion, but then as you dry it, you go to an electrostatic charge on there that's going to build the adhesion. So I think there's some great opportunities to look at that around what we can do about charge dissipation on that to get rid of some of the materials. Others of it, you got to think of mechanical issues pressed on here. So if I'm heating it up very much, I'm actually making the situation worse. Once I get above the TG, the material tends to compact into the surface of the material. So do we actually use chillers on this to actually bring the temperatures down? So I think there are a lot of opportunity to look at cause and effect on there. What's the mechanism on it?
Okay. All right. Any other questions, comments? All right. Thank you, sir.
Thank you.
Appreciate it. Yeah. Our last presenter, Dr. Jayakody, was assistant professor of the Southern Illinois University, and he's going to be talking about engineering microbes to upcycling agricultural bioplastics, and he's going to be joining us virtually. Doc, you there?
Hi, Gene. Yeah, I do.
Okay. We've got him as a pre-recorded presentation, so we're going to go with that, and then we'll turn it over to him for Q&A.
Hi, all. Unfortunately, due to a personal reason, I'm not able to join the meeting in person, but I'm very excited to share our ongoing work on applying microbial system to tackle one of the greatest environmental challenge human being face today. It's plastic pollution. So first of all, I would like to thank Jim Jones to having me today, and I, again, very excited to share our work on this field. Let me share my slide first. So today, I would like to talk about engineering microbes to upcycle agriculture. Bioplastic, I know the APRC is a recycling concept. Now, I'm trying to see what is the opportunity with the upcycling that's making more valuable product out of the plastic, especially as an agricultural bioplastic. I try to convince you the possibilities with the bio-based system today. In early 19th century, when bakelite invented the plastic bakelite, and then we started to think about a new way of life. The throwaway living. You take a food from DU 1940, in 1946 Chick-fil-A, to McDonald's 1948, Burger King 1954, and 1964 Arby's start wrapping their food with the plastic materials, and then you don't have to wash, and no need housewife to wash your dishes, right, and just take and dispose. That's the way we develop the disposable society. Now, after 5 decades, where we are at, we mismanaged plastic, especially the single-use plastic. and we put them onto the landfill, or eventually these plastic ended up in the ocean. 8 metric tons per year of plastic enter the ocean right now, and plastic in the ocean outweighed fish into the 2050. That's a prediction. We all eat, drink, and breathe plastic today, because you know that the microplastic, the degraded plastic material, coming into the micro level or the nano level and disperse into the environment. It's going through the food system, and whenever we taste seafood, you're eventually eating microplastic. You're drinking water contain microplastic, and the atmosphere right now containing microplastic, you're breathing as well. The consequences of these still unknown, but there are reports coming in that have the considerable health effect. Now, how about the agricultural system? Are we also having a disposable society concept? The answer is yes, because if you think about the mulch plastic, right, you're using in the agricultural system after the cropping season, you take that and put it into the landfill. The global agricultural plastic mulch demand has reached 7.4 million, and it has a cargo value 6.5. So this is ever increasing, right? The demand. You know, it's important for some of the crops, especially the vegetables and fruit. Now, what we can do, one thing is this plastic being produced using a petroleum-based material, isn't it? So that enhancing the effect of greenhouse gas emission. On the other hand, these are synthetic plastic not able to degrade. So that's why the last few decades, researchers and the industry trying to develop a biodegradable polymer which can use as an alternative source for the mulching instead of PE or polypropylene or like synthetic plastic. One of the popular and more attractive biopolymer is called PBAT, polybutene adipic terephthalate. The market size increasing, expected to reach about 635 million in 2023. This material shows a greater possibility to replace polyethylene. Now, the question is, all the biodegradable plastic, the main idea is after you use it should be degraded in the soil, okay? Because the soil microbes, the nature ecosystem, the microbes can in the ecosystem could able to degrade these into carbon dioxide and water and their biomass. That's the concept. And you know, if you take carbon dioxide out from this system, even you make the biodegradable plastic from petroleum-based sources, that would increase the greenhouse gas emission. Now, alternatively, you can use a renewable source material. If you take a renewable source material, that's possible to generate all these bioplastic, which are popular in the market right now, including PLA and PBAT. You able to have a renewable cycle, and that would reduce the greenhouse gas emission remarkably, isn't it? And you can also have the composting system to make a methane, and then methane, there is a C1 metabolic upcycling approaches. You can create a novel polymers out of methane as well. So this is a circular system, fine. Now, the quick question actually, could we be able to get a carbon dioxide and water completely degradation, these material in soil, especially in the agricultural field? The answer is no. So if you this is the p-band, this is the SEM image, the soil microbes able to degrade it, but they create a microplastic as well. So generally, the UV heat physically or the mechanically able to degrade the bioplastic and make this microplastic or the nanoplastic. Even the microbes now enable to do this process. They're not completely degrade, okay? Some of the microbes partially degrade and making this nanoplastic or the microplastic that could have an impact into your agriculture system. Now there are several projects running through USDA to understand the consequence of microplastic in agricultural ecosystem that could be having issue with the soil properties, to crop growth, and also changing the microbial ecosystem. So there are several ongoing research to understand the effect. In addition, lately, it says the bioplastic is toxic as the traditional or the synthetic plastic because some of the microbes in the soil able to degrade these not into the carbon dioxide and water, but they're releasing the bad chemicals which containing in this plastic, and that could change the microbial system. They could kill the beneficial microbes in the agricultural field, and it can be detrimental to the aquatic agricultural ecosystems, etc. So this is a very alarming us to think about. Okay, you cannot plow the plastic after the cropping season into your soil again because it could cause these issues, generating microplastic or adding a bad chemical or the toxic chemical into your farmlands. So what is the approach then? You have to have a recycling method or the upcycling method to bring this material into a circular economy, the bioplastic. Now, how we can do that? The way we can think about it is, one, the great potential is a chemical based recirculation that is advanced relative to mechanical recirculation. Why? Because the mechanical recirculation generally make the material with less mechanical properties in every recycling process, and it's very hard even to apply the mechanical recirculation system, as you all know, for the agricultural plastic, which is less recycled today. Now the chemical method is advanced. You can use these to create the original monomers again from the plastic and feed back into the production system to create the material again. However, we have to use a catalyst, maybe very expensive, and also the solvent to extract these chemicals. So there are pros and cons. I would give you an example. This is the work done in our group, Andrew. What we try to do is this group basically working on a chemical-based solution to upcycle plastic. PET, polyethylene terephthalate, that's also have a link to the agriculture, the food, and the beverages that we make coming through these materials. And so PET, when you take PET, polyethylene terephthalate, can be degraded into a simple monomers unit. In this case, we're using a BHAP molecule. We want to create from PET, and that can be done with the catalyst and in the presence of ethylene glycol. This ethylene glycol can be produced through the biomass based product or the petroleum as usual. However, when you get this compound, then you can do a molecule level composite with the bioderived molecule. In this case, we are using the muconic acid. Muconic acid is one of the compounds you can make through bio-base, okay? And then you can get this unsaturated polyester. That unsaturated polyester further polymerized using a fiberglass reinforced plastic. to make the fiberglass reinforced plastic. Now, this completely changed PET into a new material. This material has a better property than the PET, okay? Because adding these bio-derived molecules has a tremendous effect to enhance the material property. It's been well documented. In addition, it gives you a fivefold higher economic value if you take the recycled PET versus this new fiberglass reinforced plastic. You can have a better economy. You can reduce the greenhouse gas emission by more than 40% and the energy for the production by more than 50%. So these have a tremendous effect, okay, to the entire system of recycling or the upcycling. So that's why we're proposing these upcycle approaches. So this is chemical based, right? I told you we have to use a bad chemical, solvent, etc. Now that's why we had to think about the other approaches that are more efficient than that. In 2016, this discovery motivated myself and many of the researchers to think about and rethinking the recirculation system, because this is the first bacteria that uncovered in Japan in 2016. This bacteria called Idenella secans is able to eat PET. In other words, they can degrade PET using a two major enzymes called PETase and MHATase, and they can convert it PET into original monomer ethylene glycol and terribolate. They have a metabolic pathway to utilize that terribolic acid and survive on plastic only as a carbon source. Okay, so our enzyme team enrolled start understanding these enzymes. The first thing you have to do is crystallization, and then understand their structure, and also use artificial intelligence and machine learning techniques to further understand the molecular mechanism and uncover the mutant changes that could make to engineer this enzyme further to increase the degradation rate. Able to do that, and they create the enzyme that more faster to degrade polyethylene terribolate. The same concept applied by the French group called the Waterways, and they in recently 2020 they published this. They use a new enzyme. This is heat resistant enzyme, act on 72 degrees, that is the blast transition temperature of the PET, and they can completely degrade a plastic bottle within 10 hours. Massive, right? Massive achievement. So now these companies start already show this concept in pilot scale. They're going to have industrial scale system in Europe, especially within another 2-3 years. You and I could able to see this enzyme-based technology enable recirculation of PET. Now, in friction science, this is really good article. I know the article. Now, I would recommend you to read this. Mutant 59, the bacteria coming from other planet through meteorites into the Earth, destroy all the plastic containing materials, crashing, airplanes, and melting down all the street light, blah, blah. So this is create a catastrophic event because the bacteria that could able to eat and melt down the plastic. Now, we thought, okay, how about creating microbes, not to, destroy the planet, but taking the plastic and utilize that plastic as a material to make a new compound. So that's our goal. We started this area to explore the microbes, how we can engineer them to produce a value-added, high-value advanced molecule out of plastics waste. The idea is, okay, you're making the cell factories. So my field is synthetic microbiology. I try to engineer organisms to do this job. I look into microbes, their system as units. They have palms, you know, so you can tune those. The way I'm looking in, this is the way I look at microbes is like a genetic circuit for me, electric circuit in other way. This is a very nice image from MIT. I can adjust, I can tune, I can engineer this electric system, and like analog to, you know, I prefer here, I'm not using real ICs, but my playing material is genes, so I can tune those and make microbes to do the job which I want. So that's where I'm using the metabolic engineering, okay? So I'm feeding something, let's say plastic, I want to get a product which I want through this system. So in the first place, we take that enzyme from hydrolella and try to put into our box called Pseudomonas butyrate. This is soil microbes. And it's able to utilize most of the petroleum-derived product, okay? And have a tremendous capability to utilize several organic compounds, and also very robust in nature, this bug. So we took that and we engineered. You are seeing here the scan electron microscope images. You can see the plastic is degrading, and they're able to selectively degrade PET into original monomer. Okay, so what this demonstrate, you can actually make a synthetic microbes, and then we want to go further, not like the earlier slide I showed, the original monomer, you can recirculate like carbohydrates in enzyme purification, but we can use whole microbes to do that job. At the same time, we realize the compound that making by this microbe is very toxic to them. That's why I said in earlier, some of the compound that could release to the agricultural feed is toxic. This is an example. This is soil microbes, right? I told you. And whenever they have ethylene glycol, they kill themselves in very low concentration because they're making a highly toxic molecule called glycoaldehyde and glyoxal. So we identified this happened because of there are some of the gene. I told you I'm looking into the microbe as, you know, pump, right? And some of these microbial pumps not on. So we're able to on this using a metabolic engineering approach. It's a very classic thing. I day-to-day experience right now to feeding my kids, you know, they like vegetables pretty much, but whenever we train them, someday we start eating that. Same way we did this, and we able to have a peptide strain engineered that able to funnel ethylene glycol efficiently. They can use more than 100-fold higher ethylene glycol relative to the natural strain now. And what important, they can produce this polyhydroxyalketone compound. This is bioplastic monomer. We can get through the engineered microbes using ethylene glycol that can be further catalytically upgraded into biodegradable plastic. Now, we didn't stop at that point. We're trying to see, okay, not only ethylene glycol, there are several other organic materials there. So we had to expand the microbial capability. We expand their ability to utilize 150 different compounds, very toxic compound that can come through the plastic. And this is one example, the muconic acid. I showed you how important to have advanced polymer you can make through the cis muconic. So we can able to generate that cis muconic. This is a bioreactor, and using this engineered organism, this is able to convert high toxic material into added product. So You will learn this very soon. The article is under review at point. Now, what I want to show in this slide, this is what we present recently. Using this microbial system, you can funnel, we call the microbial funnel, you can funnel molecule from plastic, this is example from PET, into a different platform chemical, and then you can catalytically upgrade that one into a novel material. For example, nylon analogs you never able to get from the petroleum-based product, or you can make a new bio-based rubber, or you can make a new kind of a fiberglass reinforced plastic, polyurethane alternative, etc. So the tremendous opportunity to utilize microbial technology to generate these material. Now, in here, what I now trying to switch a little bit and give you an idea about this system, what we are right now using. This is oxidative hydrothermal dissolution invented by Ken Anderson. Ken and I working on developing the technology that can apply to upcycle plastic and biomass waste. So his system enable converting any organic material, including even the coal, you can dissolve using this system, only using oxygen and water, not any catalyst using this system or dissolvent. Okay, the water can be recirculated back into the system again, and we can convert it more than 90% of carbon. The microbes we now engineered, unfortunately I don't able to give you more information. After we get the patent, probably next year I can enclose more information for you. You can see this heterogeneous carbon containing material that derived from the OHD, able to utilize by this. This is a chromatograph. These peaks, mountain disappearing, that mean they're using these compounds. And we able to do a chemistry now, the biochemistry, to take these compound and convert it into a platform chemical. So this is a hybrid system. You can take the agricultural waste and including plastic, feed into depolymerization process using OHT and convert it into high value product through our engineered microbes. Now we have a project with one of the biggest green tea producing industry, the company in Japan, and we try to make a system using these tandem process to close the loop of plastic and the waste they generated to create a novel PET alternative, and this enable us to make the circular economy. And back to the PPAP. Now PET, like the PET, we uncovered several enzymes, and two enzymes we are right now using to enable selective degradation into original monomers we had through this enzyme system. Unfortunately, again, I'm not able to disclose the exact name of the enzyme, but we able to degrade these and producing these compounds. Now, that means we can create a circular economy to the agricultural plastic. For example, if you have a synthetic plastic, you can use OHT feeding into our microbes to generate the molecule that can use to make a PBAT. And after you make this PBAT, then you are able to put into your field, get it back, and feed into our engineered microbes that can selectively degrade this, and you can recreate the polymer again and make a circular economy. Not only bacteria, we now using yeast, for bread making, wine making. The yeast history is be with us, human, very much interact with yeast. So we use yeast because yeast already being used to produce pharmaceutical fuels, chemical, etc. So you can do the same chemistry to get a value-added product from yeast. We are using a different type of yeast engineered to utilize and make a value-added product, including the material from agricultural-based system. And finally, I want to share that the plastic is if you take the plastic is a mix, so we want to have a mixed plastic system bring into our hybrid system and creating these important molecule using the chemical and biological system, and then you can upgrade this material into novel materials. We actually now have a project to focus on developing a material for additive manufacturing. That is the one of the biggest market, I would say, in next couple of decades, going to be in great opportunity for us to develop this technology. So we are looking into funnel polyurethane, polycarbonate, PVC, PET into this system and enabling a recirculation of mixed waste. So finally, as a summary, we develop a microbial-based system that enable conversion of waste carbon in plastic, either synthetic or either bioplastic or the biomass even. We can funnel into this system and create a high-value product. Our technology is zero waste, green, and also energy efficient. With that, I would like to thank all my collaborators from national laboratories, enrolled, Sentia National Lab, Oak Ridge, and also my university partners, collaborators, and especially my crew. They are working very hard last 2 years with me to understand and get motivated to doing this, and our funding agencies to support this work. Finally, we have a new facility funded through Illinois State. It's going to be a state-of-art facility, biotechnological. We actually have the beer making facility in here as well. However, in the future, you may see we may making beer from plastic, and this is the way we know at, and I like to thank you all listening to me, and happy to take any question and reach me out if you want through my contact. Thank you. Hi all. Unfortunately, due to a personal reason, I'm not able to join the meeting in person, but I'm very excited to share our ongoing work on applying microbial system to
Restarted. Yeah. Yes, Pam.
My question is, I'm trying to upcycle the plastic by the enzyme application. I also know it's very hard to remove PE mulch from the field. Is there the possibility that there may be an enzyme that could be developed that would turn that into something that is actually good for the microbes in the field? So upcycling perhaps the PE mulch into something that's of food value for the microbial community.
Yeah, pretty good. That's one area we are looking in, how we can use these to enhance the microbial community in the soil, especially the agricultural field. And we also try and actually to generate plant inducing materials, which actually helping the plant growth, the growth promoting materials. So like effective microbes, that's kind of a concept being developed. But however, the other important thing we need to consider here, we are working with engineered microbes, the other term, the GMO. So they are probably an issue they are applying in environment. So the system we use now is contained environment. We make insulin, etc. These decades and decades. So similar system, I think we have to have another barrier if you bring genetically engineered microbes into the soil. So that's the only consideration we have right now.
Any other questions? All right, thank you, Doc. Thank you, our panelists. If everybody will help me thank them, I appreciate it. Tim and Pam. Just in closing, I'll be shooting everything to all the PowerPoints to PDF. Like I said at the beginning of the conference, get those out to everybody first part of next week along with the recording. So if you want to come back and watch over some of the segments. I want to thank everybody. We will probably do this again next year. I don't know exact dates right now, but I'll make sure I keep everybody abreast of what the plans are for 2022. Thank you and have a safe trip home.